at some later stage. It'll be there. And also, if you have any questions during the webinar, please use the chat functionality on Zoom to put any questions up that we can come back to at the end of the session. Okay, I think that's all the housekeeping. So brief overview. So as I said, I'm going to be giving you a brief overview of TechWorks Marine, and then I'll hand over to Steve to talk about this exciting project that we're currently doing. He'll then go into the use of satellite remote sensing. So we would call that Earth observation as well, of wastewater. This is a global issue, so it's not only an Irish issue, but we happen to be based here. So we'll be giving quite Irish-centric examples today. And then a bit of information on what sensing technologies currently exist to measure E. coli in situ in the sea. And as you'll see from the introduction, that's really the world we come from historically. And then Steve's going to go a bit more into the rationale of the project, our objectives, and maybe how you as stakeholders within this community might be interested in helping us see whether we can use satellites to assess bathing water quality. Next slide, please, Steve. So just a brief introduction about TechWorks Marine, and some of you have probably already seen these slides. We specialize in the provision of robust, reliable, secure marine data. So what does that mean? We measure between the seabed and the sea surface, and then the atmosphere for a range of different clients, generally in the areas of water quality and metoceans, so currents, waves, tides, water quality. We send that data back to our servers via either 5G or satellite. And since 2009, we've been working with the European Space Agency, linking this with satellite data. Next slide, please. So we are 19 years old this year. We are based in Dublin, in Dún Laoghaire in Ireland. We have a multidisciplinary team of electronic engineers, embedded developers to marine scientists, mechanical engineers, and data scientists and Earth observation scientists. So very multidisciplinary team where we can put together, as you can see on this image, complex buoy solutions for a wide range of clients, notably in the water, coastal engineering, and offshore renewable sector. We link this in situ data, which is collected through our TechWorks Marine Black Box, which is now a silver box on the left-hand side, which provides multi-parameter data back to our service here, which our clients can access in a secure manner. And this data can be interlinked with satellite data and numerical model data, as can be seen from the images. Next slide, please. So again, this is just another way of breaking down our end-to-end system delivery roadmap. So from the implementation of integrated marine platforms to real-time data management, as well as non-real-time data management, actually, through CoastEye. CoastEye is a data analytics platform through which we can access both temporal and spatial data sets to then provide our clients with information to manage their operations. And final slide, please, Steve. So this is a very brief roadmap of our history. So the different sectors we've been operating in and the different types of technologies. Since 2009, we've been working very closely, as I said, at bringing space data, space information of the ocean into our service portfolio, whether that is in marine renewables, in ports and harbors, or in wastewater. And linking that in with, as I was saying, our very high resolution in situ data. We're very proud to be fully HSQE certified with ISO certification. and we're also Achilles pre-qualified, which is quite important in the sectors we operate in. So I guess that's the commercial aspect of the business. And now I'm going to hand you over to Steve, as I said, who is our Earth Observation Manager, who's going to talk to you about a really interesting project we're doing to investigate the viability of developing an E. coli alert data service using Earth observation. Just a word of note, this is funded through the European Space Agency, of which Ireland is a member. And it's the first Irish project that's been funded through the open call in ESA, which is basically a call where you can submit proposals for lots of different things, and they take the ones that they think have got the most potential and are the most disruptive. So this is something we're quite proud of in-house, because E. coli is something, as we all know, that affects all of us as citizens. So handing you over to Steve now, and then we'll come back at the end of the presentation for Q&As. You're muted. No, you're still muted, Steve. The joys of technology. Yep.
And the slides are still up?
Yep.
Yeah, okay, great. Thank you very much, Charlotte, and good morning to everyone. So as Charlotte mentioned, I can give you a quick overview of the project. The project has two key aims, the first of which is to establish the probability of identifying E. coli events by development of an analysis method for the fusion of in-situ and satellite data, as well as using hydrodynamic models. And the second aim is to determine the viability of a proposed near real-time operational E. coli alert system for a broad range of users, including environmental agencies, local authorities, and of course, bathing water users. The first stage towards achieving these aims is to examine historical and current data on E. coli events to determine if relationships can be established between in situ measurements of E. coli and multi-sensor satellite observations of wastewater plumes. So in terms of the rationale, the project rationale, the release of wastewater into coastal waters can have a serious effect on public health and also on local economies. Untreated wastewater effluent released into coastal waters contains harmful contaminants. These can include fertilizer, coliform bacteria such as E. coli, intestinal bacteria, certain types of oils and metals. Bacterial concentrations in coastal waters are often very high following wastewater effluent events. Bathing water users in proximity to locations where wastewater is discharged into the sea are at an increased risk of gastrointestinal illness during and after wastewater outflow events. E. coli infection can cause serious symptoms. These include stomach pain, cramps, diarrhea, vomiting, nausea, and fatigue, and children and elderly people are particularly susceptible to the effects. So in terms of a study area, we've chosen Dublin Bay as our initial study location for this project. Dublin Bay has actually been designated as a biosphere reserve by UNESCO in recognition of its unique ecological habitat and biological diversity. However, over a 4-year period between 2017 and 2020, a total of 8.875 million cubic meters of wastewater was discharged into Dublin Bay from the Ringsend wastewater treatment plant. That's the equivalent of about 3,500 Olympic swimming pools. In 2019, there were 66 reportable events by Irish Water to the EPA. In the same year, there was 3.7 million cubic meters of wastewater discharged into Dublin Bay, which caused serious environmental and public health issues. You'll see on the right, this is an image of Dublin Bay showing a wastewater effluent coming from the wastewater treatment plant at Ringsend. You'll see that it's coming out past the Poolbeg Lighthouse and kind of heading north towards Bull Island. There's several examples of this kind of imagery. This is a Sentinel-2 image from the European Space Agency. So the key to evaluating and managing hazards posed by wastewater effluent events is the acquisition of accurate and timely data at the relevant scales of time and space. Obtaining cost-effective information on E. coli pollution in coastal waters has a high societal and economic value. The monitoring and analysis of wastewater outflow events has historically relied on in-situ sampling methods and lab-based testing. But in-situ and lab-based methods alone are not sufficient, as these methods are limited in terms of spatial and temporal extent and are often slow to produce results. Lab-based methods of E. coli detection generally take 48 hours, during which time people are still swimming, still using the water, and could be at risk, communities at risk. Additionally, wastewater outflow events are typically episodic. They have limited spatial extents and they might be missed by in-situ sampling. So what can be done? Satellite remote sensing or Earth observation can provide valuable insights. Remote sensing presents the ability to provide complementary coverage of wastewater outflow events with increased and varying spatial and temporal resolutions. The use of satellite data and in-situ measurements combined allows for a more complete analysis of wastewater events. So satellite remote sensing greatly expands the spatio-temporal monitoring coverage of the marine environment in comparison to just using in-situ measurements. Radar, thermal, and optical satellite sensors can be used to identify and analyze wastewater plumes. Optical sensors, for example, optical sensors on board satellites are capable of distinguishing wastewater plumes from ambient water masses. Thermal sensors can measure the changes in sea surface temperature associated with wastewater plumes. And radar sensors monitor the changes in the sea surface roughness caused by the dampening effect of a plume. Historically, older studies were limited by the low spatial resolution of older satellite sensors, generally in the range of 200 to 300 meters per pixel, which isn't very useful when you're talking about coastal waters. It's fine for oceanic contexts. However, there are modern satellite sensors nowadays which possess higher spatial resolutions required to allow the biophysical changes in coastal waters to be more precisely monitored. Examples of these satellite sensors include the European Space Agency's Sentinel-2 satellite and the United States Geological Survey's Landsat-8. These satellites have spatial resolutions of 10 meters and 30 meters per pixel, respectively. So optical sensors on board satellites record data in visible to near infrared bands of the electromagnetic spectrum and are capable of distinguishing wastewater plumes from surrounding water masses. Wastewater and stormwater plumes can be identified and classified by their spectral features. If you look to the images and box plots on the right, you can see the distinct spectral signatures of wastewater and stormwater plumes. This is a study that was done off the coast of California. You'll see that the wastewater plume reflects most strongly in the green wavelength of light, and the stormwater plumes have reflectance values which are highest in the blue to red ranges. Biophysical parameters can also be utilized in order to distinguish wastewater from stormwater plumes. For example, wastewater plume turbidity values are generally quite low, ranging from 1 to 10 NTU. While stormwater plume turbidity values are generally high, ranging from 12 to 50 NTU. So with specialized algorithms, they allow the biological parameters of the seawater to be calculated from multispectral optical imagery. Coastal chlorophyll A concentrations are routinely measured from satellite images. Wastewater events can trigger an observable biological response in coastal waters. Chlorophyll A concentrations derived from satellite sensors can be used to monitor the biological response to the addition of nutrient-rich wastewater in surrounding waters. Several satellite studies of wastewater events have noted significant increases in chlorophyll A during the wastewater outflow event. If you look to the images on the right of the screen, at the top, well, these images are from the California area as well during a wastewater diversion event. And at the top, you'll see chlorophyll A concentrations before, during, and after the event. And you can see there's an obvious increase in chlorophyll A. Once we get into the October image, there's a huge increase in chlorophyll A in the area. And this increase in chlorophyll A is associated with a decrease in sea surface temperature, which is noted on the bottom images, again, the before, during, and after images. So thermal sensors, such as the thermal infrared sensor instrument on board the Landsat 8 satellite, they are capable of accurately measuring sea surface temperature. Sea surface temperature anomalies can be used as an indicator of bacterial pollution in coastal bathing waters. There's a high correlation between water temperature and bacterial concentration. And then we have synthetic aperture radar, or SAR. So optical imagery is limited by cloud cover and of course by daylight hours. So optical satellites, even if they're orbiting, they cannot take pictures at night. So they're limited to the daytime operations. SAR data can help to overcome these issues because it's unaffected by cloud and sunlight, which is quite handy in a country like Ireland, where we're plagued with clouds constantly. SAR instruments SAR instruments work by imaging the planet's surface through transmitting an electromagnetic pulse towards the surface, and then they receive an echo or a backscatter reflected back at the satellite. They can function in any light or in most weather conditions. Wastewater and stormwater plumes contain high concentrations of surfactants and contaminants, which can cause a dampening effect on the sea surface. This has the effect of reducing ocean surface roughness when compared to adjacent waters. So reduced sea surface roughness will translate to lower backscatter in a SAR image. And lower backscatter will appear as a darker patch in the image. So if you look to the image on the right, you'll see Dublin Bay again, except this is a SAR image. They're not always very intuitive to look at. I've highlighted the Rings End wastewater outflow area or the plant, and in the yellow, within the yellow, you'll see an area, a darker area, which is an area of lower backscatter, which translates basically to the water there is calmer and there's a dampening effect from whatever is coming out of the outflow pipes from the Rings End plant. So in this way, SAR instruments are able to detect measurable differences in the sea surface roughness between the normal sea state and wastewater plumes or stormwater plumes or oil slicks or any other phenomenon that causes low backscatter. So SAR sensors are capable of penetrating cloud cover and operating in any light, which is great, except they do have limitations. Sufficient wind must be present for SAR to effectively identify plumes. So we need wind speeds in the range of approximately 3 to 8 meters per second. Without that sufficient wind, all the surrounding waters will produce low backscatter and it won't be possible to identify areas that are being dampened. SAR is also limited by an inability to distinguish wastewater plumes from other low wind or low backscatter regions. So as I mentioned, oil spills, surface eddies, bathymetric features such as sandbars or sandbanks, because all of these features can produce areas of low backscatter. And if you look to the image on the right, again, to the SAR image on the left-hand side, the black and white image, you'll see where the Rings End plant is. There's an area of low backscatter, which would correlate with the dampening effect. But to the south, there's areas of low backscatter on the strand, which would be sandbanks or sandbars. So in this sense, the SAR gets confused. So also high winds can disperse surfactants too quickly, and that will negate any dampening effect because the contaminants and the dampening effect has been neutralized. So the SAR sensor can't distinguish a plume if the wind is too high as well. So due to all these factors and these reasons, it's generally recommended that a combination of SAR and optical sensors should be used. In terms of wastewater detection, SAR is most often used as a part of a data fusion approach with optical imagery as well. This approach allows a more complete and detailed observation of wastewater plumes and can mitigate common issues encountered when using a single sensor approach. And just worth noting as well that those two images on the right were taken on the same day. So the Sentinel-1 overpass of the satellite was at 6:40-ish a.m. in the morning, and the Sentinel-2 optical satellite image on the right was taken at 11:45 on the same day. So you can see in the SAR image there was already some outflow coming from the plant. You can see that in the lower backscatter seen on the image, and then later in the day it was still ongoing. So microbiological methods commonly used to detect pathogenic bacteria in water, such as E. coli, generally use lab-based culture or biochemical tests. However, these methods, as mentioned, take a long time. They can take up to 48 hours to determine whether the water is contaminated or not. So there are a handful of exciting cutting-edge sensors available commercially that are capable of performing more rapid in-situ E. coli measurements, and there are others that are in development stages. One of those is the AMAS or AMAS alert system. This sensor is an automatic and remotely controlled microbiology sensor. The sensor carries out field measurements of total coliforms and E. coli. Water is sampled into a bioreactor with a reagent and growth medium, and then it is incubated. So any bacterial presence and development is monitored using multispectral instruments within the sensor. Real-time data can be transmitted to a remote server and can be monitored by system users. The system can send automatic alerts if a threshold is exceeded. And this system is commercially available under the brand name Fluidian Alert System. Another option available is the RS Hydro Proteus sensor. This is commercially available, and it's a multi-parameter probe that uses fluorescence to monitor total coliforms in real time. The sensor can also detect active coliforms as well as viable but non-culturable bacteria. Detection is made possible by using tryptophan as a proxy. The sensor can provide an indication of E. coli counts. Has been shown in studies to show a strong correlation with the laboratory data. So these in-situ sensors and others that are in development, such as the coli sense instrument by our colleagues in DCU, they present great potential to be used as part of a data fusion approach, combining lab samples, optical, thermal, and SAR, satellite data, and hydrodynamic models. So as part of this project, we will develop and employ such a data fusion methodology in order to demonstrate a correlation between high observed in-situ E. coli rates and contemporaneous wastewater plumes, and investigate the viability and efficiency of potential E. coli data alert service for a broad range of users, including environmental agencies, local councils, and local bathing water users. We would, of course, welcome your contributions in terms of available data sets or models which could be used for comparisons and the establishment of statistical relationships between satellite and in-situ data. Thank you very much, and we can go to Q&A session.
Thanks, Steve. So I've just been collecting a couple of questions here, so I can go through them, and yourself and Charlotte can respond, I suppose. The first question is from Richard Dannett. He's just asking, what volume of discharge would be required to measure a surface reaction? So just as a note that bathing waters are often impacted just by very small discharge volumes from stormwater overflows. So do we have an idea of kind of what volume of discharge will be required to see the surface reaction through SAR?
Oh, with SAR in particular, or with optical as well? Just SAR?
I guess either or both.
Okay. Let me just go back to. Can you still see the slides, Shane?
Yeah.
Yeah. Okay. So volume, we would need quite a bit. I can't give an exact number, but if you look at this image, you're talking that's about a kilometer by a kilometer, if I was to guess, that's creating that dampening effect. You can see it with less here, so you would need a few hundred square meters on the surface. Is my guess. Can't be more specific.
Yeah, and if I can just interject in that. So satellites have pixels as we have in our phone cameras. So to a certain extent, it depends on the amount of pixels. Now, pixels are becoming smaller and smaller with time. So I would expect that number to change. But in a way, that's part of what this project is about, linking in measurements that have been taken in situ of E. coli, try and see what the relationships are with the satellite data, try and understand is there a minimum threshold below which it's very difficult to pick up such events or not, and also bring in machine learning into this, to see, can machine learning help us look at common denominators or proxies to moving this forward.
And then there's a follow-up question as well from Richard, or a separate question about bathing water performance. It's generally impacted over a period of a few hours, up to a few days. Can we expand more on how chlorophyll measures could also be useful in terms of dynamic bathing water management? Maybe Charlotte, I might hand that over to you.
Yeah, so again, Richard, coming back to the theme of this work, it's all about data fusion and understanding the different relationships. So we can get several chlorophyll overpasses in any given day from different satellites that are available, so either public or private ones. And then, of course, that can be linked in with deployment of in situ chlorophyll sensors, which can then complement the time series between to bridge the gap between the hours or the days of such events. So there are mechanisms that exist at present by which you could do rapid deployment of a small data buoy with multi-parameter sensors to manage this, to monitor this type of event, let's say, happening. And that's one of the things we're trying to do with this project. At the moment, we are trying to get data in Dublin Bay every time there's a satellite overpass. But it'd be great if we could link some of our data either with historical events or events as they happen, because then that would enable us to fine tune, does this actually work? Is this worth investigating much more? Because I believe personally it is. It's just a question, there are amazing technologies out there. It's a question of putting them together and testing the hypotheses and refining them and understanding that, the real meaning of the information. I hope that clarified that.
Thanks, Charlotte. Richard has a third question as well. Are the sensors measuring tryptophan or are they culturing bacteria? I think the sensors that we've shown there are doing both. So I think the fluidian one does culture bacteria, and the other sensors are measuring using fluorescence, so they're measuring kind of indicators for E. coli rather than E. coli directly. Ronan has a question as well, asking, are the systems capable of detecting bacteria from sources other than wastewater, for instance, from rivers or just wastewater? Charlotte, I might hand that over to you.
Thanks for that, Ronan. So as Steve pointed out, different types of water sources have different spectral signatures. So my answer would be they probably are, but more work would need to be done. And same with the rivers. I mean, this project is the first of its type funded through the European Space Agency to see, can we use spatial assets to monitor E. coli. We picked E. coli because it's something that's of interest. But yes, to be able to monitor different waters coming into bays or the origins of different waters, logically, if they have different spectral signatures or slightly different spectral signatures, we should be able to do something about it, and we should be able to validate that in situ with either hyperspectral or multispectral sensors as well.
Thanks, Charlotte. Kevin has a question about the, I suppose the data that Steve was showing there. Has this work kind of been carried out on US data only, or has this approach been used for other kind of temperate waters as well? I guess what we're trying to look at, can we do it here, basically? So it's a kind of combination of both. Maybe Steve can talk a bit more about that.
99% of the literature and the previous studies done are based in California, this Southern California bight. There was one study done in Morocco, which wouldn't be very relevant. No, so California is the only examples that I've found so far. There's a wealth of literature on it. However, those studies done in California are generally only trying to detect wastewater plumes. They're not trying to detect E. coli events or trying to create statistical relationships. They're just trying to track the plumes or distinguish wastewater from stormwater. So yeah.
We also have a technical project manager, so within the European Space Agency, who's currently working on this type of research in the Black Sea as well. Black Sea. So, this is really cutting edge R&D in terms of what you could use satellite data for, and the data fusion aspects of it are still very much being developed at the moment. And so we see this as a very interesting time for us here in Ireland. With being an island nation on the western frontier of Europe, we have done validation studies of coastal satellites for the European Space Agency in the past, and we've used Irish waters over using pristine laboratory type waters in the Indian Ocean, and the data has actually been really good, much to everyone's surprise in ESA. So we would hope that our approach at actually trying to see, can we develop something in a populated area would help us, prove this right, because we need to prove it in real conditions. And that's why we went on to our doorstep in Dublin Bay here.
Ronan has a follow-up to Richard's question. Would the fresh water flows on the surface as a result of stratification potentially cause a similar damping effect?
Possibly. And again, that's something we need to study and we need to rule in or rule out. It's really very early days in this. And I mean, part of the issues is we need as much data as possible. So, you know, one of our questions to you guys listening in on this today is, you know, we're interested to work with anyone who has either in situ hydrodynamic or biological data, both present and historical, so that we can look at the data and see, do we see relationships with the satellite archives?
Sure, and that kind of ties in, I think, to Richard's follow-up question. And Richard, we really appreciate your lots of questions. There's no need to apologise for them. And we could potentially have a separate chat maybe after this. But Richard's kind of next question is, can the plumes generated by river discharges and assets, so for example the treated effluents and the overflows, can those plumes be separated out because they're both significant sources of bacteria?
Yeah, I mean, that's part of the work that we need to do, is that we need to classify the different types of plumes. So between stormwater, wastewater, or river, so that we're sure which type of plume that we're looking at. Yes, they can be using different spectral signatures, different biophysical parameters. They'll have different characteristics, but we need to find out what those are first.
And then Kevin is asking as well, can this approach be used to measure enterococci? I'm not sure if we can necessarily distinguish between the different types of bacteria, but we can kind of potentially distinguish the areas where it's more likely to be. But again, maybe I might ask Charlotte to complete that.
So once again, as I was saying earlier, we have used E. coli as a measure, but there's no reason why, if you didn't have a good handle on the spectral signatures and a good understanding of what you were looking at with in situ validation, that you couldn't make the link to other bacterial presences in the seawater or in the coastal water. Again, this is part of the interesting work. I mean, this is all very novel in terms of the approach, because as we all know, either taking water samples or taking spot samples with sensors gives us a very small spatial representation. And in a way, where satellites bridge the gap is they give us a huge spatial representation at very low temporal resolution. Putting the two together and using machine learning to help us do that, all of a sudden means that we can extrapolate into much larger areas with confidence, which is something that we don't really have at the present time.
That's all the questions. Cyprian just had a comment and suggestion there about historical data. Which, yeah, appreciate. Yeah, I don't know. Does anybody else have any other questions that they'd like to put in there? I mean, what we can do, or what I'll do at the end, is just I'll pop Steve's email into the chat box as well, if that's okay with Steve. So we're happy to kind of have, you know, follow-up questions and follow-up discussions, and we're planning to at least, you know, keep these kind of webinar series going to keep people updated as well, because once we have a better understanding of what we can detect and what we can, it's always good to kind of show it to people as well, to see how much of it is useful.
Yeah, and I think, you know, this very much is a work in progress, and we don't want to be working in isolation. And you know, we're using Dublin Bay because we're physically based in Dublin, and we have a great example on our doorstep, but we're by no means highlighting that example over any other. If we were based in Cork, we'd be picking an example there. But if anyone does have any data, and I take on board your point, Cyprian, you know, we are literally looking to use data to see, can we pick up, can we match it to satellite data? So we'd be interested to talk to all of you offline, and see. Some of you might have been involved in model studies and might be interested in seeing how the validation can happen with satellite data. Some of you might have historical E. coli data and might want to see how this could work in a specific area. We have access to very large satellite archives, and so we really are keen to have an open dialogue with this community of interest. And I think on that note, does anyone have any further questions? Yeah, take on board your point, Ronan. But again, this is part of the things we are going to look into and going to find out. And tryptophan measurements are something else that we have an interest in here, because those sensors are readily available at the moment off the shelf. So, as Sinead said, this is being recorded. Steve's email address is now on the chat. And please do make contact with him, or we can do a follow-up with everyone here. And then if you're interested in helping us or working with us to see where we can take this, we'd love to hear from you. Thank you for your time this morning. Thanks to Steve and to Sinead for putting all this together. It looks easy, but it's not so easy when you're trying to do it all, and technical glitches always happen. But I think we've done quite well. And as Steve said, we are going to be doing these on a regular basis to keep people updated as to our progress, so that we can bring it out to the community and get your feedback and your responses. And yeah, we look forward to keeping you posted. Thanks a lot, everyone.